the previous lesson we have defined the bar resolution. It is a complex with bar n equals to zg tensor n times tensor zg, and differential defined by the formula dn of an element of the form a1 tensor n tensor a. Remember I told this we will write as a1 an a. So it is free ZG module whose generators are such things where if you take a1 and an from G, so any element of here is a linear combination of such elements. And we have defined dn by the formula dn of one, so on, n plus 1 equals to two, so on, n plus 1 plus some here plus some for I from 1 to n minus 1 in the ith power of a1, so on, minus 1 ai times ai plus 1 ai plus 2, so on, a n plus 1, and the last term is minus 1 in the n plus 1th power a1, so on, an plus 1, and so we have defined on such terms, and then we can proceed by the ZG linearity. And now we discuss a little this complex. We'll transform it in different ways to get some similar complexes that are yes, and bar 0, bar 1, bar 2, so on. It's a complex, and here we have a map pi to z, where pi is the linear map from zg to z that sends any element of g to 1, since bar 0 is zg. Yes, and this data defines a free ZG resolution of Z. Well, there are some similar but little different complexes that define free ZG resolution of Z2. One of them is the so-called normalized bar resolution. So this complex is called bar resolution, yes, and also it is called sometimes unnormalized bar resolution. So what is normalized bar resolution? Normalized bar resolution can be obtained in the following way. Sorry. It's later. First, I'll recall that Hn of GA is by definition tor of Zg from Z to A, and Hn of GA by definition Ext over Zg from Z to N to A. So in other words, we can apply the tensor product to the bar resolution. So it is bar dot tensor over Zg A, and then take the nth homology, or here we apply the home factor. It is bar dot home over Zg from bar dot to A. If we apply appropriate definition of what's this, it's a complex, yes, and take then homology now. If you look at bar n, yes, then we will see that bar n tensor over Zg A is by definition Zg tensor n tensor Zg tensor over Zg A, and we can cancel one copy of Zg, and it is isomorphic to Zg tensor n tensor A, yes, and the differential, which is d bar tensor A, yes, written in these terms is of A1, so on, A, let be A, and A n plus 1 tensor x is it's here, yes, it is A2 an plus 1 tensor x plus sum for I from 1 to n minus 1 with ith power A1, so on, AI plus 1, so on, AN plus 1, that's our X, plus A1, so X minus 1, and then plus 1 power, so on, AN, tensor AN plus 1. X and what about the second one?
So we just act on the first part and on X is trivial.
What?
So we just act on the first part.
Here
Yes.
you multiply X by this. And what about the second one? There you can see that bar M home over Z home over ZG bar M A is by definition home over ZG G and tensor G A that is isomorphic to home or Z from ZG tensor N to A, and in these terms a differential D bar home ZG bar A M. Now we need to apply it to some element of this home, so apply it to F and then apply it to A1, so on, AN plus 1. Yes, what's this? It is first F of A2, so on, AN plus 1, then the sum for I from 1 to M, F of A1, so on, AI plus 1, so A N plus 1, and plus, minus 1 and I power, plus minus 1 and the N plus 1 power, F of A1, so on A N times N plus 1. And now what is normalized bar resolution? It is obtained in the following way. We can consider the complex bar and tilde, the complex with terms bar and tilde, where bar and tilde.
So what is the home 1 through? Why is this isomorphism of homes? Yes.
What?
Why is it true?
Why it's true? As minimum from the conjugation, yes. Home over ZG extends over Z, yes. ZG A is isomorphic to home over Z X home our ZG from ZG to A, and this part is isomorphic to A. And this isomorphism is conjugation between tensor and Hom functors. So bar n tilde is a submodule of bar n generated by elements of the form ZG submodule, yes. By elements of the form A1, so on AN, where for some I, AI equals to 1. Yes, and generate our ZG. Then it's easy to see that bar tilde is a subcomplex of bar, because when you apply dn to an element of the form A1, so on, A minus 1, 1, AI, so on, an plus 1, yes, you get some big sum where you have so on, 1, so on, yes, and only at 2 summands you have another thing, exactly for I minus 1 and for I, yes, here plus 1, yes. So for I minus 1 you have minus 1 in the I minus 1th power an ai minus 1, ai plus 1, so on, an plus 1, because you multiply a minus 1 by 1. And for I you have the same thing, because you multiply 1 by I plus 1 and they cancel, yes. So bar tilde is a subcomplex of bar, and so we can moreover the map Sn that we have defined on the previous lecture, yes, we have defined Sn from bar n to bar n plus 1, such that like for n more or equal to 1, one has what, dn Sn plus s minus 1 dn minus 1 equals to id bar n. It is that module of homomorphism. And this map Sn simply took element a1, so an a, and sent to the element a1, so on, n a. Yes, and it's easy to see that that Sn of bar tilde lies in bar tilde, and hence bar tilde is exact. So the homology of bar tilde is 0, and if we take the factor complex then we still have free resolution of Z. Which is called normalized bar resolution. Normalized bar resolution. So in fact, bar n simply zg factor z as a z module tensor n tensor of zg tensor zg. Yes. So you simply take this factor instead of simply zg, and the differential is the same. So you only multiply classes. So from this we see that in fact, for example, any element in homology can be represented by a map F from bar from the normalized bar resolution yes to A, and then we can take the composition and get a representative via bar resolution, and this representative will satisfy the property that F any element of N GA can be represented by a cocycle F from bar N to A such that F of bar tilde is 0. So F is 0 if one of its arguments is 1. From here on, we also will use the following notation. We will denote by Cn of G A. It's the elements of bar and tensor over ZGA, yes, by, but usually written via this isomorphism by Zn GA will denote cycles, elements of Cn GA that are annihilated by the differential and by Bn GA boundaries. So elements of Cn that lie in the image of the differential and analogously we will denote by Cn of GA the nth term of the complex Hom bar A by Zn of GA will denote cocycles etc. Elements of this that are annihilated by the corresponding differential and by Bn GA coboundaries.
We wrote a formula for Cn and C.
What?
We wrote a formula for Cn, but there is no such formula for cycles and boundaries, right? So small formula, like. But we just named them, but we didn't say anything about them.
About cycles and boundaries?
Yes.
Well, these elements that annihilate by differential.
So you can write something, but it's too long.
There is some formula for differential. I can write like elements such that and write, but
It has no.
it will take a lot of place and time. At some point we will write something, I think. So there is one more form of bar resolution which is called homogeneous bar resolution. It is the same resolution, but like it is resolution isomorphic to bar resolution, but written in another way. And as I understand, people who study algebras would prefer this bar resolution that we have defined, and probably people who like groups would prefer this one. So the elements of bar resolution of bar n are linear combinations of the elements of the form a1, so on, an, a, yes. And to this element we can put in correspondence the element a1, so on, an, a, a2, so on, a, an, a, so on, an, a, yes. So here the element is an element of ZG tensor n tensor ZG, and here it is ZG tensor n plus 1 that is the same, but here we write in this way to point out that the ZG model structure is here, yes, and here all components are like in the same row, yes, because if we denote this by bn, b1, this bn plus 1, then the G module structure is on this resolution. Is defined by the equality one, so bn plus 1 times g equals to b1 g, so bn plus 1 g. For G and G. Yes. Oh, probably I'm a little wrong. I think that here we need to have elements from G2. So such elements constitute Z basis of Bn, yes. So we can define a map of Z modules in this way.
Y equal to? Y is equal to?
It's G.
Oh.
And B1, so on, Bn plus 1 are from G2. So it is a Z module with this basis. And the differential is defined by the equality dn of b1, so on, bn plus 2 is equal to what? To the sum for I from 1 to n plus 2. E plus 2 is minus 1 in the here in the I plus 1 power b1, so on, b I minus 1, b I plus 1, so on, b plus 1 plus 2. Yes. So you simply drop down some element and put some sign and take the sum. And in this way, it is like more symmetric in arguments, so it's called homogeneous. And if you want to consider the normalized bar resolution, for normalized bar resolution, one also put b1, so b plus 1 equals 0 if for some I, bi equals to bi plus 1. This corresponds exactly to the occasion that some gi is here, I think, gi plus 1, yes, is equal to 1. Yes. So, in some sense, this form is more beautiful, but we'll use what we have defined before. Now, one application of bar resolution is the form theorem. Suppose that G is a finite group of order m. Then sorry, m times hm ga equals to m times hn of ga equals 0 for any G module A and any n more equal to 1. For 0 it's not true. Proof. let us define phi n from bar n to bar n plus 1 by the formula phi n of and it is a ZG module homomorphism. Phi n of A1, so on AN. Or not, sorry, 1 minute. Yes. So AN is the sum for all G from G. Since G is finite, we can do this. G, A1, so on, AN. Yes. Since these guys are more or less generators as ZG modules, as a ZG module of bar n, we can do this and proceed by ZG linearity. Then let us calculate the following thing. Let's calculate dn phi n plus phi n minus 1 dn minus 1 of A1, so on AN. Yes. So it is dn applied to the sum for G from G, G, A1, so on AN, plus phi n minus 1. Now we apply dn minus 1, so it is some sum cheaper 2, so on AN. Yes, plus sum for I from 1 to n minus 1, minus 1 in the ith power, A1, so on, AI minus AI times AI plus 1, so on AN, and plus minus 1 in the n plus 1th power times A1 AN minus 1, yes, AN.
Should there be R minus 1 into N?
What?
Should there be minus 1 in GPN?
Yes. You're right. So now we apply dn here. Yes. Since the order of G is m, you first get what? You drop G, yes, m, and take the sum m times. So you get m, A1, so on, AN. It's the first what you get. Then you get the following thing. You get the sum over G from G of the following guys. The first guy is minus sorry, here, minus G A1, A2, so on AN. Yes, then you get the sum for I from 1 to n minus 1 minus 1 in the ith power, or not. No, for 1 you yes, since you put here g, it is shifted, so for 1 you get 1, so I plus 1 g a1, so on, ai plus 1, so on an, plus minus 1 in what power? In the n plus 1th power, I think. G a1, so on, n minus 1 an. Yes. And now you apply phi n minus 1 here. Yes. First you get, well,
is it n plus 1 or n again? Is it again n?
No, here n plus 1. Because you put g here. We have put. So everything was shifted. So it is again the sum for g from g. Like this guy, it is g a2, so on an. Plus, and you can see that it is the same thing as here, but with the opposite sign. Yes, it's easy to see. Here you put g, and you get the same guys, and here I plus 1, and here I. And here you have n, and here n plus 1, minus 1 and nth, and n plus 1th power, but you again put g here and get the same thing. So this guy cancels this, and now one can easily see that this and this, when you take the sum for all overall g, is the same thing. Yes. Well, because you may assume that a1 is from g, and the element g times a1 in this case go through the same set as g. Yes. So this guy cancels too, and you get simply m a1 so on an. And this means exactly that
Can you read again why the last one cancels?
Hmm?
Can you read again why the last one cancels?
this.
Yes.
Well, if you're interested in generators of bar n over that g, then you may assume that a1 and an all are from g, yes. And then ga1 goes through the same set as g when g goes through g. So you can check this on generators first. So what we get? We get that the multiplication by m map from bar n to bar n is equal to dn phi n plus phi s1 d s1. So in some sense the multiplication by m on the whole resolution here n more equal to 1, yes. In the opposite case you will have some problems with this summand. So in some sense the multiplication by m on the whole resolution is homotopic to 0. In fact, no, because for n equals 0 it's not true. So it's almost multiplication by m map. For like you can apply this phi n and see what happens in 0 degree, and you will see that it is like multiplication by m map in all degrees except 0. In 0 it is multiplication by m plus something else. And so what? So multiplication by m map on C star of GA and C star of GA is almost homotopic to 0, 2.
Is this notation accurate when we multiply the homologies by m?
What?
Is this notation accurate when we multiply the homologies by m? Shouldn't we take the homologies of the
Of what?
of the function of multiplying by m of g? Shouldn't we first apply to g the function which multiplied by m?
To g?
Yes.
What is g?
We have a map from we have a map from bar to bar.
And like almost means that there is some map which is in all degrees except 0 in multiplication by m, but in 0 degree we don't know what, and it is homotopic to 0. Yes, like this map. But when we apply a home functor or tensor functor, and this means that and the multiplication by m map from Hn of GA to itself and from Hn of GA to itself are induced by the multiplication by m map here and here, yes, on C and C. And since this map is null homotopic, on homology it is 0. On Hn of GA and Hn of GA for n more equal to 1. More equal to 1 exactly means explains this term almost, yes, because 0 degree is it is not null homotopic. Well, now we go to the next topic. It is group extensions. An extension of G by A. So G and A are arbitrary groups. Is a short exact sequence of groups. A, E, G of groups. As usually, extensions A, E, G, and A prime G are isomorphic if there exists like phi from E to E prime such that the diagram A, E, G, A, phi, prime, G commutes. In this case, of course, phi is an isomorphism.
What do you mean in this case?
If there is such phi that this diagram commutes.
So it is always
What does mean always?
if extensions are isomorphic.
Yes, if extensions are isomorphic, then this phi is isomorphism. So our problem now is to describe all extension of A by G. But such an extension, except A and G themselves, has another data.
Does it always exist?
Hmm?
Does it always exist?
Uh,
An extension.
Extension, if you are interested in arbitrary extension, yes, of course, because you can put E equals to the direct product of A and G. So, yes, sorry, I forgot. At first, we will consider, at this moment, and we will consider the case of abelian A. Later we will see what happens in the case where A is an arbitrary group. And if A is an abelian group, then it is, of course, can be considered as Z module. But if you have an extension, this extension gives you an action of G on A, because A is a normal subgroup of E. So there is an action of E on A that, of course, given A a structure of E module so there is this action is defined by the equality x times E equals to E minus 1 xe for x in A, E in E. Yes. And since A is abelian, if E is from A, so A is a subgroup of E, yes. So if E is from A, then x times E equals x, and hence this E module structure induce G module structure. on A. So if G is from G, for G from G, sorry, let us denote this by alpha and beta. Yes, for G from G, we have and for x from A, have x times G is equal to e minus 1 xe, where e is such that beta of e equals to G. And as I explained before, the definition doesn't depend on the choice of E. Yes, because different choices of E differ by some element from A, and an element from A acts trivially on yes, acts trivially on A.
What is beta projection?
Beta is here introduced. Sorry, the problem is divided into stages. Yes, first you have to look at all G module structures on A, and we will not do this. We will be interested in the second stage, where you already have A, G, and G module structure on A. You have A, G, and G module structure on A. So we want to describe all extensions of G by A, inducing this structure, this G module structure. Yes, in particular, if you choose a trivial G module structure, then this problem will be reduced to the problem of describing central extensions of G by A. Central means that A lies in the center of E. Well, of course, if A and G are given and G module structure is given, the question is if there is some extension, and yes, one extension exists always exists the skew semi-direct product extension A G A G. What's this? Where G semi-direct A is equal to G times A as a set, and the product is G A times H B equals to GH, and here AH plus B. Sorry, I forgot to say that the operation in G we will write as multiplication, and since for a while A is abelian, the operation A we will write as a sum. So AH comes from the G module structure, yes, and this is an operation of A. I think you know this construction of a semi-direct product.
And AH comes from the G module structure.
What?
A times H comes from the G module structure.
Yes, yes. So now the extension A E G is called split if there exists it's alpha beta sigma from G to E, which is a homomorphism of groups, such that beta sigma equals to IgG. And probably you know that extension is split if and only if it is isomorphic to the semi-direct product extension. Do you know this or not? It is like if you have semi-direct product, then of course it is split because here G is a subgroup, and you can simply send G to G0, yes? And I think that in the general course of algebra there is a criterion that a group is isomorphic to the symmetric product of like A and G if A is a normal subgroup, G is a subgroup, and their product is all E, something like this. No? Like A is a subgroup, G is a subgroup, and they generate all the group. Then the group is and their intersection is trivial. Then the group is a semi-direct product. Well, if you don't know this, it would be exercise. So in one direction it's trivial, yes. In another direction, it is not very difficult to. You simply have sigma, yes, and you can write any element as sigma of G times alpha of X, yes, and in this way you get such pair, and you can check that these pairs are multiplied exactly by this rule. So now let us take an arbitrary extension. Let now A alpha E but G be an arbitrary extension. Then there exists sigma from G to E. Now it is not anymore a group homomorphism, but it's simply a set theoretic map. Such that we still have beta sigma equals to IgG, yes? Because beta is still surjective independently of what extension we have. And well, we can choose sigma in different ways, but for convenience, we choose sigma in such a way that sigma of 1G is equal to 1E. Yes, we can do this because we choose it element by element, yes, and of course beta of 1 is 1, so for 1 we can choose preimage 1.
Is A still a billion?
Yes, yes. Like from now on and until I will say we will consider only abelian extensions by abelian group, and when we will consider extensions by non-abelian group, it will not call it A anymore. We'll call it X, or I think X.
WJ sigma.
Sigma is set theoretic splitting of beta.
Yes, but
And we choose it in such a way that sigma of 1 is 1. We can do this because like 1 is a preimage of 1. So now we still can write the group, any element of group E of E can be written uniquely in the form sigma of G times alpha of X. Yes. Because this the sequence is exact. Yes, so if you have some E in E, you simply write it as first you take sigma beta of E, yes, and then you write sigma beta of E inverse times E, yes, because if you like this guy is of course sigma of something, yes, and this guy, if you apply beta now, you will get 1, yes, because beta sigma is identity, so you will get beta of E minus 1 times beta of E. So this guy is from A, from the image of alpha. This one is from the image of sigma. And if you like elements in the image of sigma do not go to 1 if they are not equal to 1. So if you take two such guys and write the equality that 1 equals to 1, then put alpha to one side, sigma to another side, you will get that they are the same, this and this. That so any element can be written in such form in a unique way. So still E, of course, as I said, is A times G. Is G times A, as I said. So it remains to understand what's the multiplication. So you multiply sigma of G, alpha of X, and you want to multiply by sigma of H, alpha of Y, yes. Well, you want to get sigmas there and alphas there. First, you can, since A is normal in E, you can transfer sigma to the left in the standard way. Simply write sigma of G, sigma of H, sigma of h minus 1 alpha of x.
Sorry, can you explain the first?
What?
What do we do right now? So we have an element.
We want to multiply and again write it in this form: sigma of something, alpha of something.
So it's two elements. So e.
What?
First, sigma of y times alpha of x is the first element of e, and we multiply it by another element of e.
Yes. So sigma of h alpha of y.
We have two y's.
What?
We have two y's, but they're different.
Where are two y's? It is g.
Oh,
It's g. G. So this guy is, by definition of our action, is exactly alpha of xh. Yes. So here we have alpha of xh plus y, and it is some part that already was in the semi-direct product, but here we still don't have sigma of something. So if sigma was a group homomorphism, then it would be simply sigma of gh, yes? But now we can't write sigma of gh, but let us try. So we will write sigma of gh, sigma of gh inverse, sigma of g, sigma of h. And if we look at this, yes, and apply beta to it, we will get 1, yes, because beta sigma is identity. Yes? Beta sigma is identity, we apply beta, we get gh minus 1, gh, and it's 1. And this means that this guy lies in the image of alpha. So this guy equals to alpha of f of gh for some map f from g times g to a. Yes. And so we get finally our formula. So here you have sigma of gh times alpha of gh, alpha of f of gh. You can put alpha outside and get f of gh plus xh plus y. And so the formula for the product is the product is if you multiply g x by h y, you get gh, and here you get f of gh plus xh plus y for some f from g times g to a. But it's not clear if any map from g times g to a give us a group structure. What we need to check? have a group structure.
Associativity.
Associativity, yes, of course. So, let you believe that if we will have associativity for such elements, the opposite one. That if we will have associativity for such elements, G0, H0, and let be T0, then we will have associativity for four elements. So let's write this guy. G times H, it means that you take GH, and here you get f of GH, and you multiply it by T0, so you get, of course, GHT, yes, and here you get what? You get f of GH T plus f of GH T, yes. So now let us write in another way. Let us write this and multiply these guys. You get HT, f of HT, and when you multiply here, you get simply what? GHT. So the first components are equal, of course, and here you get f of GHT plus f of HT. And now let us write what we get. Called star. The operation star determines a group structure on G times A if one has so the first components are equal, so we need to equalize these components. So let us do this in the following way. F of HT minus f of GHT plus f of GHT minus f of GHT equals 0 for any GHT in G. So is it similar to something or not? Well, in fact, if you have a map from G times G to A, yes, then you have an induced map from ZG tensor ZG to A, yes, and even Z linear map. So if and only if the corresponding map, let's call it F from ZG tensor ZG to A. What?
We already have map F.
This map is induced by F. F is from
It's like F star.
F tilde is a two-cocycle. F tilde is from Z2 GA. So probably you remember that when we compute the group homology, we apply hom to the bar resolution, and like the second term is exactly maps from ZG tensor ZG to A. And if you apply the corresponding differential to F and evaluate it on the triple GHT, you will get exactly this. Well, so I think that the time is finished. And of course, spoiler that you can choose different sigma, yes, for the same extension. And different sigma will determine different f's, but the maps corresponding to the same extension will differ by a coboundary. So by a map from that comes from differential from the G to A. And in this way, we will have a correspondence between extensions and second homology.